third unit is energy and momentum. We're going to do energy in this video, momentum will be in the next video. And we start this unit off discussing work. Work happens when a force moves a distance. So say I'm pulling on a rope connected to something and I move at a distance, I do some work. Now, sometimes you have to separate the physics term work from what you're used to, your normal definition of work. So here, if I hold a 100-gram mass above my head for an hour, I didn't do any work. Why not? Well, even though you would say maybe to your friends, holding that mass up was so much work, in physics, the force has to be moving a distance. So if you're just holding something stationary, the work is zero. Also, if the force is perpendicular to the displacement, we're not doing any work. So let's say you have this is a top view of your car. Let's say your car breaks down, and you push it. Let's say forward for a quarter of a mile, and you have some friends pushing the car this way. Well, they're doing work because their forces are in the same direction as the displacement. But if you're pushing the car this way, as it rolls forward, you're not doing any work because your force is perpendicular to the displacement. Another way to find work is the area under a force displacement graph. So let's try the first work problem. Go ahead and pause the video and try the problem on your own. Okay, you should have attempted this problem on your own. The horizontal force F is used to pull a 5-kilogram block across the floor at a constant speed of 3 meters per second. The frictional force is 10 newtons. What is the work done in 1 minute? Okay, so from the last unit, you should remember constant speed means the forces are balanced. The normal force is balanced with the weight force, and your push force is balanced with the friction force. So work equals force times displacement. Your push has to be equal to the friction force, which is 10 newtons. So 10 newtons. And the problem doesn't give me the displacement, but it does give me a speed, 3 meters per second, and a time, 1 minute. So I know that the distance is equal to speed times time. So I'm going to make that substitution. And the speed is 3 meters per second, and the time, convert that to seconds, is 60 seconds. And so I'm going to get an answer of 1,800 joules. Kinetic energy is simply the energy due to motion. The nice thing about energy, and the big difference between this unit and last unit, is that energy is a scalar, meaning that it only has a magnitude. So we don't have to worry about directions for the most part. We don't have to break vectors into components. That's what makes energy nice to deal with and a nice way to solve problems. So here's our kinetic energy equation, 1/2 mv squared. And the units for energy, work, are joules. The work energy theorem says that the net work, the total work that we do, is equal to the change in an object's kinetic energy. The way that I find the net work is I can do this two ways. First, I could find the work done by every single force and add them all together, add all the works up. Or I could find the net force and just find the work done by the net force. Whichever one you choose is fine. When the net work is positive, our object speeds up. When the net work is negative, the object slows down. And if there's no net work, there's no change in kinetic energy, and we have a constant speed. Give this work energy problem a try. Go ahead and pause the video now. Okay, let's take a look at this problem. Under the influence of a force, a mass of 4 kilograms accelerates from 3 to 6 meters per second in 8 seconds. How much work was done? So I see that there's a change in speed, and it's also asking about work, so that makes me think, let's use work, kinetic energy theorem. So the net work is equal to the final kinetic energy minus the initial kinetic energy. And the net work equals 1/2 mv squared minus 1/2 m v naught squared. Simply just plug the values in. 1/2, the mass is 4 kilograms, and the final velocity is 6. Got to square that. Subtract 1/2 times the mass times the initial velocity, which was 3. Square that. 36, so I have 2 times 36, 72, minus 2 times 9, 18. Or it looks to me like 54 joules. Okay, now power is the rate the work is done. It's how fast the work is done. So work divided by the time. Let's say that I'm going to pick up a package and lift it up above my head. Now I can do that very slowly, or I can do that very quickly. Either way, the work is the same, but the power is not, because the power depends on how long it takes. We can also express the power as force times velocity. The unit for power is the watt. So give this power problem a try. Go ahead and pause the video now. Okay, let's take a look at this power example. A child pushes horizontally on a block of mass m, which moves at a constant speed v across a floor. The coefficient of friction is mu. At what rate does the child do work on the box? Now, anytime you see rate, that means over time. Okay, so at what rate does the child do work? That tells me it's work over time, which equals the power. I have 2 choices to find the power. I can do work over time, or I can do force times velocity. Since it tells me that it's a constant speed v, I'm going to use force times velocity. So power equals force times velocity. Since we're moving at a constant speed, up equals down, and right equals left. The push equals the friction. So the power equals friction, which is mu times the normal, times v. So here's my force of friction, and that's not an answer choice, so I have to go one step further, and the normal force equals the weight. So mu mg times v, or choice A. Now, if you ever look at your power bill, you'll notice that we buy energy in something called the kilowatt hour. That's how we're billed. Now the kilowatt hour, so kilowatts are power, and hour of course is time, and if you multiply power times time, well, power is energy per time, and we're multiplying that by time, so the times cancel out, and kilowatt hour is just a measure of energy. Okay, it's just a measure of energy. And a kilowatt hour, if you want to know how much energy it is, it's 3.6 times 10 to the 6 joules. It's a nice exercise to figure that out. Another type of energy is potential energy. Potential energy means stored energy. We can store the energy two ways. One is gravitational potential energy. That means we're storing it with height. The second way we can store energy is elastic. That means we're storing it with a spring. Conservation of mechanical energy tells me that as long as I have no friction, no air resistance, mechanical energy is conserved. All the potential plus kinetic at the beginning of a problem is equal to all the potential and kinetic at the end of a problem. So the last three problems are conservation of energy problems. Go ahead and give those a try. Pause the video now. Okay, you should have tried all these conservation of energy problems. Let's go through them. First one, a rock of mass m is thrown horizontally off a building with height h. The speed of the rock as it leaves the thrower's hand is v0. What is the kinetic energy of the rock just before it hits the ground? So we're going to use conservation of energy. Kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Then think about, what does the rock start with at the beginning? Well, it has a height, so it has potential energy. It has a speed, so it has kinetic energy. Then it falls towards the ground just before it hits the ground. That's what we're interested in here. It has a speed at the end because it's moving, it's been falling, it's going to be moving faster. But it doesn't have a height, so it doesn't have potential energy, so I'm going to cross that out. We're looking for the kinetic energy of the rock before it hits the ground. So we're looking for the final kinetic energy. Well, that's just equal to all my initial kinetic energy, 1/2 m v0 squared, and all my initial potential energy, mgh. Going with choice D. A block of mass m slides on a horizontal table, frictionless, with a speed v0. So I have some block that's moving with speed v0. It compresses a spring, so it's moving towards a spring. And it comes to a stop. So the block comes to rest, and the spring gets compressed by some amount, x. How much is the spring compressed? That's what we'd like to know. So we set up conservation of energy, 1/2 m, kinetic energy initial plus potential energy initial equals kinetic final plus potential final. At the beginning of the problem, it's moving, so it has kinetic. There's no compressed spring yet, and there's no height, so I can cross that out. At the end, it comes to a stop, so I have no kinetic. And now we have energy stored in a spring, elastic potential energy. So I do have potential energy here. I'll put in the equations. 1/2 m v0 squared equals 1/2 k x squared. Multiply both sides by 2, cancel the 1/2s, solve for x, which is the displacement of the spring. X equals the square root of m v naught squared over k. I can pull out the v naught. X equals v naught times the square root of m over k. Choice D. Last problem. A block of 3 kilograms is hung from a spring, causes it to stretch 12 centimeters at equilibrium, meaning not moving, as shown above. Then a new block is released, and we want to know how far will it fall before reversing direction. Okay, so this is an energy problem. We're starting with potential energy, gravitational, and we're ending with potential energy, elastic. We're turning height, call this h, we're turning height into the energy of a spring. Okay. And what we're looking for here is, what is this height? So mgh equals 1/2 k x squared. But what you have to recognize is that h and x are the same. So mgh equals 1/2 k h squared. So one of the h's cancels. And so h equals 2mg over k. And I know the weight. The weight's 40, 4 times 10, but I don't know the spring constant. So this is a two-part problem. Part of it's energy, but the other part, I have to find the spring constant, and this part is an equilibrium problem. So I'm going to set up a free body diagram. Right here, I have mg, my weight, and I have a spring force, F of s, spring. And I know that since this is stationary, the up equals the down. So kx equals mg, or k equals mg over x. So real quickly, the spring constant is going to be 30 over 0.12. 30 over 0.12. Okay. So that's what is that? That's about 250. Spring constant is about 250 newtons per meter. So I'm going to use that over here, and I'm going to now plug this in for k. So the height is 2 times 40, this mass, over 250. So what does that give us? That gives us 80 over 250, which is 8 over 25. That's approximately a third. Yeah, approximately a third. So I'm going to go with, so it's about 0.33 meters. And so my best choice that I see is 32 centimeters.